before he grew his beard and his horns. So I worked as a DBA and developer. I wrote a few books on Oracle, one on MySQL. This presentation is somewhat a summary of what's in this book, Oracle Performance Survival Guide, which is, to be fair, an 11G book. It's not been updated for 12G, but it still contains most of the sort of the detail for this. And I contributed to the Oracle Exadata handbook that's coming out, I think, next month. I'm an Oracle ace. You can find me here. GuyHarrison.net's my website. There's a page on that website that's got lots of articles. There's a lot more information, excerpts from the book and things like that are all there if you're interested. And I'm Guy Harrison, all one word, at Twitter. And that's my Dell email address. So about Dell, you all know who Dell are. We make laptops, and you probably know we make servers as well. You might not know that Dell is the biggest independent provider of database tools. And this happened when Dell acquired Quest Software a few years ago, Quest Software being the company that produced Toad. Now, the story of how Dell acquired Quest is a complex one, but I've summarized it up in this little animation. I think we might not have sound here, but let's see. So there was Quest with the Toad product, and there was Dell. Quest wanted to go private. Dell wanted to buy a software company, and so consequently it went something like this. You've got to imagine Pac-Man noises there. And Dell acquired Quest. Sort of against our will, but we're very happy at Dell. Dell's putting a lot of investment into the Toad and the other database tool, and it's good to be part of something bigger, frankly. So that's enough about us. Let's get on to the top 10. Everyone who submits presentations knows that if you put the words top 10 in your abstract, you've got a much better chance of being selected. I suspect it's because top 10, it sounds like you're going to get 10 things, which is a lot, and they're the top 10 things, so they're going to be good things. So there's sort of like this subconscious thing about it must be good. But, you know, 10 things in 1 hour means 6 minutes per thing, which isn't very long, and I've already wasted a bit of the time, so it's going to come down to about 5 minutes per tip, which means that these have to be fairly high level, right? It's not going to dive deep into each topic. I'm just going to introduce each topic, and hopefully it gives you an idea about things that you might want to learn more about. And I've tried to organize it around a sort of a methodology. So you'll see here are the 10 things. Be methodical and empirical, optimize your database design, index wisely, write efficient code, optimize the optimizer, tuning SQL and PLSQL, monitoring and managing contention, optimizing memory, tuning I/O last, but tuning it well. And I gave this presentation in New Zealand a few months ago, and no one picked me up on this, but those of you who are very numerate might notice those are only 9 tips. And so I had to add one for this presentation because I realized that I'd ripped them off. And the last one is to understand RAC and how to tune RAC-specific performance topics. So let's get into it. Being methodical and empirical. So this is why I think the most important mental thing of all when you're trying to tune Oracle databases is to take a sort of a scientific, data-driven approach. So by methodical, I mean that you've got some sort of plan of attack. You're not just sort of like randomly changing parameters or doing a sort of like code and fix or trial and error thing. And you're doing hypothesis and experiment. In other words, you've got a theory about why the database might be running slowly, and then you're going to test that theory. And that sort of testing of the theory really implies that you're empirical, empirical being a word that means using data. So we're always going to measure performance. We're going to measure it before and after. One of the things that is absolutely critical but often overlooked is to have a control group. So this is, you'll see this every now and again as someone says, I rebuilt the table using this parameter and my query time sped up by 50%. Okay, great, but what if you'd rebuilt the table exactly as it was? And then often you find if you just rebuild the table, your query time goes up 50%. You just pack the table into a smaller number of blocks, there's less I/O or what have you. So always make sure that you've controlled for every variable. And beware of people like me, old DBA tales and sort of silver bullets. People like me, and there's a lot of us hanging around that have worked with Oracle since Oracle 7, have got all these sorts of things we learned through bitter experience, but for all you know, they don't apply anymore. And so always be very critical of someone's past experience, especially if it relates to a previous version of Oracle or it's on some different platform, or even it's a different application, a different workload. You know, these rules of thumb, they're useful, but don't take them as gospel. Okay, so in my view there are two main ways to attack Oracle performance in a methodical way. The first one is the one that you hear probably the most about, which is performance troubleshooting. And this is the method in which you basically are looking at whatever part of the application you're concerned about and trying to work out where it's spending the most time. And then when you've found out where it's spending the most time, try and reduce that time. So this is System R, if you've heard of YAP, yet another performance profiling methodology. Just a weight-based analysis is very heavily biased towards this sort of performance troubleshooting. You look at a trace file or you look at feed or system event, you see there's a lot of latch weights. You decide, okay, the thing for me to do is to try and reduce these latch weights. And that's fine, but it's kind of a bit reactive. You've waited until the performance problems happened before you've actually started to do anything about it. Another approach, which is more sort of proactive, which is to tune your database by layers. And you're pretty much doing the same thing, except you're taking into account the fact that you know that the database and the application work in a sort of a layered way, and you sort of start from the top and work your way down. Now, what do I mean by starting from the top? Well, let's have a think about how a database request happens. Essentially, you've got the application which sends SQL down to the database server. The database server's got to parse that SQL, compile it, prepare it for execution, and then it's got to go into Oracle memory, and it'll try and find whatever it needs in memory if it can at all. And then only if it can't find it in memory will it go to disk. And then after it's gone to disk and it's gone to memory, the data, it sort of flows back up back to the application result sets and so forth. Now every layer, if you think about it, the load on memory is dependent on the type of SQL you're sending. The load on disk is dependent on the type of caching you're doing. And all of that is dependent on the amount of contention in the database server, the amount of work the database server can get done. And so it sort of makes sense to work downwards because each layer depends on the layer above it for its workload. So you start by tuning your SQL, trying to reduce the workload. Then you start looking in your RDBMS and in the database code itself for contention points, things that are sort of like bottlenecking. After you've done that, you can start to look at memory to make sure that the logical I/O that gets through that contention is being satisfied in memory as much as possible, and then and only then do you go and tune your I/O. The troubleshooting methodology might suggest to you that you want to start with your I/O first, but it's almost always a better idea to work with your workload, your SQL tuning, and so on. To put it another way, in a simpler way, what's wrong with this donkey, right? Why is this donkey not getting any work done? And you can start talking about feeding the donkey better, or putting the donkey on an exercise program, or hitting the donkey with a stick. None of that's going to make much difference. The problem here is clearly the workload. There's too much on the cart. And so, to put it very, very simply, start trying to take stuff off the cart first. Try and make Oracle work smarter rather than harder. I haven't got a lot of time to talk about this in detail, but measurement's an important part of that, and there's lots and lots of tools. Dell creates tools. Toad's got a lot of stuff in it. Spotlight's a tool within Toad that I've worked on a bit. And obviously there's OEM and other third-party products. But even if you've got none of those, you can get a lot of information out of Oracle just with a few SQL queries. I would say that 90% of performance problems can be identified with maybe 3 or 4 queries, and this is one of them. I know you can't probably read that, but it's there on my website at guyharrison.net, and it's just a join of VDOL system event and VDOL assist time model, and it's telling us pretty much where the database workload is concentrating on, and it gives us a good idea about where to start. Okay, that was number 1. So number 2 is database design. There's really not a lot you can do 1 year from now without rewriting the application from scratch to change it. So it's very important that if you do have control over this, that you get it right. Now the first point, and I know this is kind of basic, but the starting point is generally third normal form, where we're really eliminating all of the redundancy in the data model and using the sort of the adage, dry, don't repeat yourself. Within third normal form, there's a lot of choices you get, and a few of them can be very significant. We'll talk a bit about that in a minute. And after third normal form, you do denormalization, where you're actually repeating data, creating sort of, this is snapshots and materialized views of denormalization. There's plenty of denormalizations you do to try and improve your workload. But don't start with the denormalization. Try and work your way through third normal form, because otherwise you risk getting an inconsistent model. So third normal form, again, I realise most of you, or maybe all of you know this, but it's worth sort of like going over it, I think. is mostly a matter of removing redundancy. So here we've got some data. It's students and tests and questions in the test. And we don't really want to type the student name in every time they take a test. We don't want to repeat the test every time for each student. And we don't want this repeating group of answers because it makes it very hard for us to get average and sums and things like that. And we might be wanting to add questions later on. So when we normalize it, it looks something like this. Students take tests, tests have questions, and students that take the tests have answers. And this is a very, very straightforward data model. The thing I want to press on this, if you're ever doing this, is don't go too far. This is a good example of going too far. I hope you can see this. This is the MySQL Sequela sample schema. It's like a DVD rental store. And if you see over here in customers, what they've done is they've said, well, more than one customer might live at the same address, so I'm going to pull address out of the customer table. And then addresses, some of them have the same city, so I'm going to put city out of the address table and I'm going to put it over here. And then cities are in countries, so I'm going to have a foreign key to a country table. And for some reason they stopped there. I don't know why they didn't go countries are in planets and planets are in solar systems and solar systems are in galaxies and galaxies are in universes, universes are in multiverses or whatever. But they stopped there, thank goodness. But they'd already gone way too far because now we've got this thing where every time we want the address, we've got to do 3 joins. And that's just going to be a load on the database that's going to exist in perpetuity from this point on, right? They'll probably never get a chance to sort of pack that back in. So just make sure that you use a bit of common sense on things like that. Another example of this database design principle is subtypes. So the typical example is customers are people and so are employees. So they have a lot in common. And so when we create our customers and our people and our employees, do we have 3 tables? One with the common stuff, another with employees, another with customers? Do we have one table with the things that are customers nulled out for employees, or do we have 2 tables where we repeat a few columns? Now it depends on your workload, but it's almost always better to go with the version that requires the least amount of joining. And this is the one that generally requires the least joining because you're pretty much always writing queries against employees or customers. So there's not much point in doing the other 2. This one's almost always the worst one because every time you access anyone, you're going to need to join. Okay, and then denormalization, which is a huge topic, so I'm just going to put the definition of it here. But it's the process by which we take all this third normal form, elimination of redundancy, and then start going the other way, specifically to improve performance, adding redundant data or adding grouped aggregate data so that when a query comes through, it doesn't have to do a join or it doesn't have to do a group by. And Oracle gives you like tons and tons of tools. Partitioning is a sort of a denormalization tool. Materialized views are another great one by which we can do this. Okay, on to tip 3. Excuse me. Indexing. Again, it's a sort of like a basic topic, but again, it's indexes are there mostly to improve performance. And so getting the best set of indexes is absolutely critical. And the biggest basic fundamental skill is making the right set of concatenated indexes. You want to have a set of indexes that cover as much ground as possible, but not too many because they slow down transactions. Obviously, we think of indexes like an index on a book. That is to say, when you read the whole book, you don't read the whole book by going to the index and going to entry A and flipping back and flipping forward and flipping back. You just start the book and you read from the first chapter through. But if you're looking up something specific, you tend to go to the index, and obviously that's the same with Oracle tables. We want the index only when we're looking for a specific piece of information. Now, concatenated indexes where we have an index on more than one column, this is the key to good indexing. So just as an example here, if we're looking for this query down there, customer ID from customers based on name and date of birth, that's the performance with no index. Here's just an index on last name. It already seems pretty good, so sometimes we sort of go, okay, that's great. You know, I've improved it 20 times. That's enough. But if we add first name to the index, and then we add birth year, and then if we actually add what we're looking for, so we don't have to go to the table at all, we're down to 3 logical IOs. So even though we've got a huge performance improvement with the first index, we still had 20 times more performance gain we could have got if we'd added more columns to the index. So If you see an execution plan and it just says you're using an index, that's not necessarily where you want to stop. Again, a fairly obvious consideration, but one that we sort of forget sometimes, is each index adds a lot of overhead to DML. And so as we're tuning queries, we go, okay, the solution to this query is to add an index, and then you start getting sort of so many indexes that your problem becomes inserts, updates, and deletes. And deletes especially get really, really tied up in index maintenance. So be careful. Okay, and that just sort of shows you how it works. The primary key index is much more efficient than any other index. It's much easier for Oracle to maintain it. Okay, and then another thing, which is an old DBA's tale, I suppose. If I asked you what percentage of the tables should I use an index, if I'm reading 10%, should I use an index, 20%, 2%, 1%? You might have some figure, and it used to be that a lot of people would say it's 10% or something like that. This chart, which is quite complicated, is to try and prove there is no one cutoff point. This is the amount of time it takes to full table scan. This is the amount of time it takes to use an index on sorted data without caching, and down the bottom we've got the percent of the table. So you see at around 15% it no longer makes sense to use the index. But if the data was unsorted and entirely in the buffer cache, we actually get a pretty good index performance up to about 50%. And then if we have a full table scan using non-direct I/O and it's all in the buffer cache, the cutoff point is only 2%. So it could be anywhere. You won't know until you've done your workload. So in trying to make a decision about should I use an index or should I do a full table scan, the only way to be sure is to do both, repeatedly and measure them. Okay, on to number 4, I think, application code. Now again, I know a lot of you, if you're DBAs, you don't have much control over application code. But if you are a developer or you do have the opportunity to look at how the application is structured, again, it has more impact over the performance than anything you can do later on. You can add disk and you can do this and that, but if the SQL is a bad SQL or if it's accessing the database in a dumb way, there's not a lot you can do. So there are 3 main guidelines for coding against any relational database. And one is to do as little as you can. Don't call an SQL statement if you don't have to. Maybe you can keep the data in your application code. If it's just reading sort of like a department code, it's not going to change over the course of your transaction, so you don't need to read it 20 times if you've got 20 transactions. You can probably just read it once. And then also to reduce the amount of parsing, and this is basically by using bind variables, the number 1 sort of good coding technique. Transactions, your goal here is to minimize the duration of the locks you held. Locks obviously prevent concurrent access to the database, and you don't want to hold them any longer than possible. And then network overhead, the pulling and pushing of data across the network needs to be minimized, and this is mainly done by using Oracle's array interface. So let's look at them real quickly, one by one. Bind variables are the opposite of this statement. So in this statement here, you see someone's issuing an SQL from within Java, and they're concatenating in the customer ID. They're just creating a new string and sending it to the database. And every time the database sees this string, unless cursor sharing is set, it's going to think it's a new SQL. It's going to parse it. It's going to take out a latch. It's going to find a slot within the shared pool. A huge amount of overhead. The alternative to this is to use the same SQL statement with a different parameter. So here you see we've called the customer ID :cust ID, and in the set-in statement later on we're setting it before we send it. In this case, Oracle knows it's the same SQL. I've got the same execution plan. I don't need to create a new slot in the shared pool. I don't need to take out a latch. I just need to sort of like change the parameter and execute it. The difference in performance for simple SQL statements like this looks typically a bit like this for just one process. So that's sort of like a 3-to-1 performance improvement. But it would be even better if there were like thousands of people executing this statement at once, because then those thousands of people would be contending for latches and the performance could get horrifically bad without bind variables. So bind variables, programmers who don't use them need to be educated. Transaction design is what I talked about before in reducing lock duration. So we've got 2 main locking strategies. The pessimistic strategy, which says, I think someone might change the data while I'm using it. I'd better lock it before I do anything and then commit. The optimistic strategy says, I don't think anyone else is probably going to touch this data, so I'll leave it unlocked, but just before I finish my transaction, I'll just check to make sure that no one updated it. So in this case, the duration of the lock is the entire transaction. That's pessimistic. And in the optimistic strategy, it's only for the last couple of statements in the transaction. So the duration is a lot lower. So why wouldn't you always use optimistic? Well, if your optimism is misplaced, if people are updating it all the time, you'll have to retry. And those retries might drag down performance. So you do have to have a good sense of how likely it is that another process will come and change the data underneath you. But generally speaking, we prefer to try and program optimistically, even though it's a little bit harder in code because it tends to give you better throughput. And then finally on this topic, network traffic. Round trips to the database can add a lot of overhead. You sometimes don't sort of like realize exactly how much overhead is going on, but the network is a sort of like a physical limitation on the amount of work you can get done. You know, electrons have to fly through the wire and come back. And so if you're doing a query when you're pulling lots of data, Oracle gives you a means of pulling all that data in one block, in one network packet. Or you can pull them one at a time. Now this is mainly determined by code, and there are some parameters that you can set sometimes in a client tool. But here in Java you see it's this fetch size parameter that controls the number of rows that come back in a single operation. And if you want to think of an analogy like this, it's like if you had 20 people on one side of a river and a rowboat that fit 10 people, and you started taking them across the river one at a time. That would be so incredibly inefficient. Obviously, you want to fill up the rowboat. In the same way, obviously, you want to fill up the network packets. You just want the least number of network packets possible. And this is the sort of performance improvement you get as you add array size. So it's array size along the bottom, and it's elapsed time along the left. And even a relatively small array size will increase performance manyfold in a typical situation. The other point about network traffic is complex transactions. So if you think of a transaction that goes backwards and forwards, like this one is supposed to be like an ATM. I'm transferring data from one account to another, and so I'm checking the balance in one, checking the balance in the other, changing it in one, changing it in the other, checking the log, checking a log, doing an audit trail, commit. And so it goes backwards and forwards many times. This would be a good example for where you could maybe write the whole thing in a stored procedure and just have one round trip to the database. Again, you've got to have control over the application, but if you do, this is one way to write a more high-performing application. Okay, so that's the end of the bit in which we're talking about the control over the application. From now on, we're going to talk more about things that you can do perhaps as a DBA, starting with the optimizer. So the optimizer is the part of the Oracle code that determines how an SQL statement can be executed. I'm sure you all know that. The optimizer works from a bunch of inputs, the table and index structure, so it looks in the data dictionary, is there an index? You know, obviously it can't use an index if it doesn't exist, and object statistics. And it uses these two things to try and work out how many rows it's going to have to access. Then it looks at the database configuration and parameters to work out how much logical I/O and CPU that's likely to be. And then it looks at something that's relatively new called system statistics to try and work out how much CPU and I/O I've got on my hardware. So this is some sort of like a little mini benchmark that Oracle can do now to work out that on this particular piece of hardware, CPU is cheap but I/O is expensive, or the other way around. So if you put an SSD in, for instance, it could change the optimizer's perspective. And so the bits in white here are the bits that we get to control. And so we should be giving the optimizer the best possible inputs. Now, this is a whole topic in its own right, but I'll just focus on one little bit, which is histograms. So histograms is one of the things that we have the most choice about creating or not creating. And if you think of a histogram, it's telling the optimizer how the distribution of data is. So in here, these are customers by country. And obviously, there's a lot of people in the United States, not many in Saudi Arabia. And if we wanted to get Saudi Arabia, we'd want to use an index. If we wanted to get the US, we wouldn't want to. So how does Oracle know what we're doing unless the way to tell it is to create a histogram so it can make a determination. So here's an example of a query without a histogram. Oracle thinks that there's going to be 377 rows returned and uses a full table scan. Actually, there's only 75 rows returned. Once we create the histogram, Oracle's estimate is spot on. and now it knows, because this was New Zealand, this particular query, it knows there's not many people in New Zealand, so it uses the right index. So that's just sort of like an example of giving the optimizer the information it needs to do its job. And here there's a bunch of DBMS stats calls that the main ones I think that you should become familiar with if you want to be, effective at giving the optimizer the right inputs. Okay, sort of barreling through, I know, but I don't want to be running out of time at the last minute, so I think we're about halfway through. So, and this topic, so I wrote a whole book on tuning SQL, so obviously this is a huge topic, and even now I think you can write sort of more than one book on tuning SQL. The practice has become so enormous. But the essence of the thinking here is that no matter how good the optimizer gets, there'll always be SQLs that it can't optimize. So I've been around Oracle for 25 years or so, and each release has the optimizer gets better and better. And by now it should be so good that we don't need to tune, right? It seems maybe it will get that good soon. But what happens, every release also releases some new features, some new SQL syntax or new partitioning options or new, or there's new hardware or, anyway, the optimizer is always one step behind the new features. That's been my experience. So the new SQL syntax in 12c, I bet you the optimizer doesn't fully understand it yet and won't till version 13. In version 13, there'll be some new features the optimizer doesn't explain. So no matter what happens, there's always seems to be SQL that needs tuning. And the essence of it is, how do we find the SQL that needs tuning, and then what do we do to fix that SQL? And the finding is basically using the tools that Oracle gives us. We have tools features in Toad that exploit these interfaces. Obviously, the database control and OEM has them, but there's base VDOLAR tables that tells you most of what you want to need. And then there's a host of techniques, including rewriting the SQL, but a whole lot of things that help you change the SQL without actually having to go in and rewrite it. And I'm actually not going to say much more about it because it's such a big topic that I couldn't even think of anything more to fit in 2 minutes. Dell would kill me if I didn't mention, oh actually I've got ahead of myself there. This is a good query for just if you don't have any other query, if I didn't have any other query, this is the one I'd run. Again, I know you probably can't read that from there, but it's on my website at guyharrison.net, and it's just using VDOLAR SQL to rank the top 10 SQL statements by elapsed time. And there's stuff in VDOLAR SQL and VDOLAR SQL plan. It's 99% of the time you'll find the SQL that's causing you a problem in there. That other 1% you'd use SQL Trace or some other mechanism. Anyway, what I was going to say is that Dell would kill me if I didn't mention that we have a SQL tuning tool called SQL Optimizer, which his whole point of is to find these SQLs and give you ways of changing the plan and applying that plan into production. And obviously Oracle offers a lot of a capability there as well in the tuning packs. So you've got a lot of commercial options as well as just using the underlying primitives to get the job done. Okay, so at this point, I like to think that we've done everything we can to lighten the load for the donkey. So what have we done so far? We've tuned our database design so that we don't have to do unnecessary work like unnecessary joins. We've tuned our application code so that we're not dragging data across the network or pushing too much pars down or holding locks too long. And we've looked at our SQL statements and we've made sure that none of them are too inefficient and so forth. Now's the point where we do need to look at the donkey and say, okay, is the donkey healthy? Is the donkey, got enough muscle? And maybe the donkey needs more motivation. So, and the first point of that is to look at contention. So contention is the proverbial bottleneck. In other words, when someone says bottleneck, I've got a bottleneck, they mean that there's some form of contention here. So demand comes in from the application, and we've sort of made that demand as low as we possibly can. But if Oracle can't get through that demand, can't process the requests fast enough, then the demand coming out the other end is reduced, just like the water coming out of a bottle would be reduced, and that's why we call it a bottleneck. And so this contention is for limited resources. Serialization is another term that we use for this. And there's three main categories of contention that we experience in Oracle. First is locks, and we talked about that a bit already, but we'll come back to it just very briefly. And the others are latches or mutexes, which are two words that express a very similar mechanism, and then buffer contention for buffers in memory. So locks are what we talked about before and are mainly got to do with how the application holds resources, holds locks on tables. There are internal locks though. Oracle takes locks out on the data dictionary. There's locks that, for instance, control when you allocate a new extent to a segment. Sometimes you will see these internal locks show up, but most of the time locking problems have got to do with application code, and if you want to fix them, there's very little you can do other than go back to the application code and look at the locking strategy. Latches and mutexes are kind of like locks, except instead of protecting the relational data, they're protecting data and memory. They're like very lightweight locks or serialization mechanisms that protect memory. And buffer contention is related to latches, but effectively means that for whatever reasons we can't get access to the buffer and memory that we need when we want it. So let's look at latches first. I'd highly recommend, if you want to know more about latches, that you look up Craig Shallerhammer. He gave an excellent presentation earlier this week. It's online at orapub.com. He's great at explaining the internals of latches, which are quite complex, and I'm not going to try here. But as I said, if we have multiple processes wanting to access the same area of memory, and this includes just reading it, not just updating it, but if we just want to even just make sure that we've got a piece of memory that doesn't shift around underneath us, we have to take out this latch. And only one latch at a time. Sometimes latches protect more than one block of memory, but at the most optimistic, if we all want to access the same block of memory, we'll have to take out the latch and we'll have to wait. And latches don't sort of queue up. Your access to a latch isn't based on a point in line. It's based on more of a spinning algorithm, keep trying, keep trying, keep trying, which creates sort of like a bunch of side effects, including that sometimes latch contention causes a lot of CPU burn. So you might see latch-free waits, but you also might see CPU burn. And as I said, if you want to understand this more, Craig Shallerhammer's a great guy he's a great explainer of this stuff. Buffer contention, sometimes buffers are protected by latches, or they almost always are, but there's other types of buffer contention that aren't really latch related. So free buffer waits is the easiest one to explain. When we read from the database file, so we read from a block of data in disk and we put it in the buffer cache, and then later on we can get it out of the buffer cache instead of having to go to disk, right? That's pretty basic caching. So that's all good. When we read from the disk and change a buffer, we change it in the buffer cache and it becomes dirty. We call a modified block a dirty block. And then the database writer process wakes up every now and again and clears the buffers out by writing them down to disk, and it's all good again. Now, if the buffer cache fills up with modified blocks, then you can't bring any more blocks into the buffer cache. It's got nothing to do with latches at this point. You know, like yes, you can get the latch, but unfortunately the database writer hasn't finished writing out all the stuff. So that's, at that point, you get a free buffer wait. It's a very common occurrence if your database writer can't write fast enough. And that can happen if for some reason your I/O system is better at reading than writing, then free buffer waits are kind of almost inevitable. And this can happen with RAID 5, and it can even happen with SSDs, because SSDs read a lot faster than they write. So you get this free buffer wait scenario. It's pretty easy to induce anyway. You can definitely make it happen if you create a situation in which reading's easier than writing. So that's an example of buffer contention. And here's a couple of weights that you will see relating to some of these things. Free buffer wait, the ones at the top there are cache buffer change latches. The library cache mutex and library cache mutex in particular, this is the one you see if you've got no bind variables. If everyone's trying to parse simultaneously, it's almost certain that you'll see library cache contention on the latch or mutex. There's a parameter cursor sharing that you can use if you can't get people to use bind variables that kind of sort of like inserts bind variables into the code on the fly. Okay, so that's contention. So once we've relieved contention, we sort of like opened the gates. The workload can get through now. We reduced it to start with. Then we removed contention so that the workload could get through. Now we want to make sure that the workload doesn't hit disk, because disk is going to be slower than memory. Even if it's SSD, it's still slower than memory. So we want to optimize memory to avoid I/O. Now, memory is used in Oracle I mean, there's lots and lots of memory areas in Oracle, but it still comes down mainly to two main bits. The buffer pool, which avoids I/O to the data table space, data and index and whatever, to your data, and then the PGA, the program global area, the local memory, which avoids I/O to the temporary table space when you're doing sorting, hash joins, and other hash group operations. So the text just repeats what I just said. Now, what I want to point out here is that we tend to automatically think of the buffer cache as the thing that's avoiding I/O, but it's important to remember that you can easily do more I/O from sorting than anything else. So this is a full table scan, and this is the amount of I/O to pull all the blocks off the table, right? So there's a certain amount of I/O that you have to do, and then there's a certain amount of CPU that you do to sort the data. So I'm basically select star from blah blah blah, order by whatever. And then depending on how much memory in the PGA I've got, this additional I/O can occur. So if I've got enough memory to do it all in the sort in memory, everything's good. As I run out, I have to start writing to the temporary table space, and then I have a single pass sort. So there's sort of a plateau where, okay, I had to go to the temporary table space. And then if there's not enough memory for me to do just one pass to disk, I have to do more than one pass to disk. It starts to sort of like magnify out. And PGA is complicated. You can have less PGA memory than you think. You allocate, 2 gigs, and there's a certain amount of parameters that sort of prevent any individual session from getting as much as that. So keep an eye on it anyway. That's essentially what I'm saying. Now in Oracle, since 11G, Oracle's given you the option to do automatic memory management, which moves data between the SGA and the PGA based on workload. And it's a great improvement because honestly, doing this stuff manually was almost impossible. However, at least of 11G, and I haven't repeated this in 12C, but I'll be pretty confident that this still happened, you can have scenarios in which the automatic memory management goes bad. So here's an example where the workload's kind of cyclic, and every now and again something happens that makes automatic memory management push the entire buffer cache out of memory. Those are those sort of like orange spikes there. And here's another one. Now this is a really sort of like strange circumstance. This wouldn't happen very often. But in this case, it's pushed both the PGA and the buffer cache completely out of memory. This was just one PLSQL program working with MTS, and it had a large pool, and the large pool took over everything. My recommendation on this, the one thing I found that was very important, is yes, use automatic memory management, but set minimum values for each component. There's never a circumstance in which you want the buffer cache to go away completely, right? Or I would argue there's never. So you can just say automatic memory management, my total memory is, I don't know, 10 gigabytes. I want the buffer cache to be at least 1 gigabyte. I want the shared pool to be at least 2 gigabytes. And then you give Oracle half the memory to play with. Don't give it all of the memory to play with because something like this could happen. Okay, and so now we're coming towards the end, I guess, and we're at to I/O, which is a big topic. And we tune it. I hope by now I've convinced you that we tune I/O last. And if we'd done I/O first, we would have done I/O when we had this huge workload from all these badly tuned SQLs. We would have had all this contention that was possibly stopping that workload from getting through, and memory, maybe it would have been satisfying in memory or not, but we didn't check memory, so we didn't even see if we could avoid the I/O through changing the buffer cache. So to tune I/O before we've done all those things is probably not a good idea. But once we've done all those things, then we're probably at the point where we're finding that I/O is one of the major components of our workload. It'd be kind of weird if it weren't, because we are a database after all, so that's back. Okay. Sorry if we dropped off there on the internet, but it says we're back, so let's keep going. Okay, so I/O tuning. I/O, even if you're using SSDs, I/O is still the slowest part of the database. Everything else is working in nanoseconds. I/O is happening in milliseconds for spinning disk and microseconds for SSD, but it's still orders of magnitude slower than every other part. So we have to make sure that we tune it. But first we have to tune everything else. So I'm repeating myself a bit there. I'm not in third normal form myself at this point. It's somewhat denormalized. Okay, So magnetic disks, the principles from magnetic disks are pretty straightforward. The amount of I/O that you can support in your database is effectively driven by the number of disks that you have. And almost always with DBAs, one of our biggest struggles in life is to convince the person who's signing the check that we want to buy disk by the I/O and not by the gigabyte, right? How many gigabytes of disk do you need? Well, I only need 1 terabyte of disk, but I need 20 spindles. 20 spindles, that's, 40 terabytes. You said you only want to, I'm sure a lot of you have been through that discussion. It's a battle you have to win, though. You cannot afford to buy disk by the gigabyte. And even if that means the disks aren't filled with data, in fact, as I'll show in a bit, it's best that the disks aren't filled with data. So magnetic disks do between 75 and 150 IOs per second. If you know how many IOs per second you think you want, then you can do a back-of-an-envelope calculation and say right away this is the number of disks I want. And here's the IOs per second from a bunch of different types of disks of different cost too. So there's about 2 to 1 between the fastest disk and the slowest disk that you can buy. Not counting SSDs, we're still completely in the world of spinning disk at the moment. Now, latency is a different consideration. It's related, but it's not the same. So latency is the amount of time taken to do a single I/O, and most disk drives do that between 5 to 10 milliseconds. In fact, most do it under 5 milliseconds unless things are sort of bad. The latency increases with the throughput, though. So this chart is supposed to show that. So if I've got some disks and I'm trying to drive I/O up and I don't care about latency, then I can probably push these disks up to 400 IOs per second. But for some of the I/O requests are now going to return in 90 milliseconds. And for an interactive application, that's just not going to be acceptable, right? That's a tenth of a second. So, if I need my latency to be at 20 milliseconds, and I've got to keep my IOs per second down somewhere more like 200. So understanding that trade-off between latency and throughput is essential as we're dealing with disk I/O. And so this is like this graph is a good illustration. Actually, I'll back a bit. The latency also is best if the disks are not full. The reason is because the outer parts of the disk are sort of spinning faster. So if you think about the head when it's at the outside, the amount of data moving underneath the head is more per second than in the inside. So if you just have data in the outside, you'll get more data sort of flowing off the disk, and also your head won't be moving. There won't be as much seek distance. So mechanically, the disks work better if they're like 50% full or 1/3 full. And this is the hot segment thing you sometimes see in ASM. It'll just position the data in the hot part of the disk. So to get the best performance, we want to keep them under moderate load for latency and sparsely populated. And obviously we want to stripe and mirrored. We do not want RAID 5, right? Because that sort of adds a whole other complexity. Anyway, that graph there, that's the hockey stick, right? If someone says avoid the hockey stick, which is a way of saying at some point you can't get any more I/O out. You put more load in, all you do is push up latency. Your throughput does not get higher. And if you let yourself go up that hockey stick, then you're just creating poor response time for no improvement in throughput. The good part about all this is that this part is at least very mathematically predictable. You can sort of like speak with great conviction about how much I/O a disk can do. Now, spinning disks obviously have been around with us for almost forever, and they've got smaller and denser, but the spinning disk mechanical design didn't change for a long time, and Moore's law was not affecting disk speed because, and this is some charts just showing that the latency for getting data off disk and the seek time went down a little bit, but not in Moore's law thing. Mechanical devices don't go to Moore's law. If Moore's law had been applying to spinning disks, the outside of this, I'm not kidding, this would literally be true, would have to be moving faster than the speed of light. So that can't happen, and it didn't even nearly happen. Mechanical devices increase geometrically, electronic devices sort of improve exponentially. So this was a sort of a problem for us, which was resolved somewhat by solid-state disk. So solid-state disk compared with magnetic disk, which might do 4,000 microseconds, that's 4 milliseconds to get a piece of data. Even a cheap SATA flash drive will do that in 80 milliseconds. An expensive PCI flash will do it in 25 microseconds, and DDR RAM, which is basically memory with a battery attached, will do it in 15 microseconds, but we don't really see DDR RAM. So this is great. The challenge for us DBAs is that although it's getting cheaper to get a solid-state disk I/O, and it's giving us better I/O economics, we're also challenged by this era of big data to store more and more. And yes, solid-state disks are dropping in price. So this is per gigabyte, dollars per gigabyte, and the grey line is cheap solid-state disk. The grey line is expensive solid-state disk. The orange line is cheap solid-state disk, and the blue line is a hard disk drive. And it looks like, you know, it's getting better and better. Eventually, it'll be as cheap as disk. But if you graph this, oh, sorry, press the wrong button then. If you graph this logarithmically, you'll see they're not really catching up. Spinning disk is going to remain cheaper per gigabyte, which means if you're doing very large databases, you're probably going to have to mix the two together. And working out how you mix the two together is a new skill. And some of the things Oracle's doing with heat maps and stuff is sort of moving towards helping with that. But we need to have a hierarchy of storage devices. We need to put our hot stuff on flash, our cold stuff on spinning disk. But some things will go away. DDR SSD and fast disks are probably going to sort of like disappear. We'll mainly be dealing with flash, memory, SATA disks, and perhaps Hadoop as a sort of like an offline store. But for some databases, they'll fit all on flash and then life is beautiful. But what I'm saying is for another category of databases, we'll need to remain on spinning disk. Here's an example of some performance improvements with a Fusion I/O card, which is an expensive solid-state disk. Without the solid-state disk, this is what we were doing using a fast SAS disk for random I/O. We put in the next one up, we put the Fusion I/O card in and configured it as Oracle Flash Cache, and that gave us a great improvement, roughly 4 times improvement in throughput. And then, but if we put the entire table on SSD, providing we've got enough space for that, we went down to 5% of elapsed time. So these are truly fantastic improvements in performance, and I wouldn't even think about having a database running all on spinning disk in today's day and age. It doesn't make economic sense. Full table scans. This chart is showing that full table scans aren't accelerated by the flash cache. There's a bunch of stuff about this on my website, guyharrison.net. I did a lot of work on flash a few years ago, so if you're curious, you can read up on that. The Oracle Flash Cache is only available if you're using an Oracle operating system, which means Solaris or Enterprise Linux. So for a lot of us, it's not really applicable. Here's a good chart showing us how we can use Flash to accelerate sorts. So you remember the chart we saw before where we had memory sorts, single pass, multi-pass. If we put the temporary table space on solid-state disk, those multi-pass disk sorts become much, much nicer. And so using solid-state disk for temporary table space is actually a really good idea. The one thing where I found that solid-state disk doesn't help as much is redo logs. The sort of sequential write operations to redo logs don't suit solid-state disk all that well, and they do suit spinning disk because the head never has to move. It can just write it as fast as the disk is spinning, whereas in solid-state disk there's a whole lot of physics around erasing blocks and garbage collection, and if you do a redo log type workload, it might not work as well. This is a controversial, I get a lot of argument back about this. However, no one's published data that has data to specifically show huge improvement on redo log that I've seen. Okay, so this is tip number 10 with 7 minutes to go, so there'll be a few minutes for questions hopefully. And the last one is to understand rack. Everything we've said so far applies to rack, but rack has a few additional considerations. And to illustrate those, I'm going to use this picture, which is Spotlight on Rack, a Dell product that I designed actually, that shows you this is a 3-node rack cluster. Up the top is the interconnect and global cache, and down the bottom is the I/O subsystem. So it tries to show you, how the data is flowing through the rack system and so forth. But here I'm just using it to illustrate the point. Rack works really well, providing you just watch for 3 main things in my experience. One is that the time it takes you to get a block across the interconnect, that is, if you want to get a block from another node, instead of getting it from disk, you better hope that getting a block from another node is a lot faster than getting it from disk. Because there's a lot, if you know the internals of the rack, you know there's two-way, three-way weights. There's a lot of overhead in asking for the block off the other node, and it's possible that if you had really fast SSDs or if the interconnect was misconfigured, that it took longer or at least close to the same amount of time. So you want to see something more like this, where it takes 12 milliseconds to get it from disk and only half a millisecond to get it from the interconnect. So that's good, and you just want to make sure that that remains true. Secondly, in most scenarios, you want your rack cluster to be reasonably well balanced in load. If you've got 3 nodes and 2 of the nodes are doing all the work, then you've got a bunch of problems. You're not going to be able to scale to a 4th node. Also, you'll see different symptoms from different nodes. The node that's under heavy load might show up as having latch contention. The node that's under light load might show up still as having a lot of rack-related weights because it's waiting for blocks from the busy node. So try and spread the load as best you can. And there's a couple of techniques for that, but yeah, there's a whole there's an article on Toad World specifically about rack tuning by me. So if you Google Toad World rack, Guy Harrison, you'll probably find it, and it goes into a lot of detail about that. And then finally, in rack, you want to be looking at the rack-related weight events and making sure that they're not adding up to a significant amount of time. I mean, the rack cluster, you don't want the cluster to be working all the time coordinating itself. You want it to be doing work for you. And so in this case, you know, the cluster overhead, which in this case 26%, seems reasonably high, right? You certainly wouldn't want it much higher than that. Anyway, that's sort of like rack in a sort of like 2-minute nutshell. So before we take questions, just my final pitch for Dell software. Toad is a product that's been around an awfully long time. It's awfully popular. We count something like 2 to 3 million users of Toad worldwide, including freeware users, though we've got well more than 1 million commercial users. And we have Toad products that support pretty much every database technology there is. Plus the Toad family includes tools for SQL tuning, database diagnostics, space management, data modeling, benchmarking, and obviously PLSQL development, debugging, profiling. Everything that I've talked about today and everything I ever talk about is kind of like my day job, is to sort of make sure that Toad and other products like that do these things effectively and add value. So certainly I'd like to assure you that we're still doing that with Toad under Dell. And if you don't use Toad, to encourage you to check it out, especially if you're moving into any other database technology, because we're producing things in Toad for all of that. Dell, as a vendor of hardware, has configurations for pretty much every purpose. We sell boxes pre-configured with anything you want, SQL Server, Cloudera, Oracle obviously. We have reference configurations. We're partners with Oracle on some of these configurations, pre-made rack nodes that are perhaps, you know, we would argue have substantially better value for money compared with Exadata. And that's it. That's my total pitch time. So I make it that we have maybe 5 minutes for questions, and I've got a few on the internet, but I'll take some locally first, and then I'll check the internet feed. So any questions in the room? Okay, no questions in the room. Okay, so I'll let you go if you want to go. Otherwise, I'll do some of the internet questions. Thanks very much for your time and attention.